Electromagnetic induction was independently discovered first by Michael Faraday in London in 1831 and then by Joseph Henry in New York in 1832. Michael Faraday then went on to use electromagnetic induction to build the first electric generator and the first transformer. The equation that describes electromagnetic induction is called Faraday's law, and it is one of the four Maxwell's equations. Here is the first transformer that Michael Faraday built. It is on display at the Royal Institution in London. We are going to build and demonstrate some transformers. I will also explain how they operate. Transformers have many applications. They are used to step up or step down voltages. They are used for impedance matching. They are used to produce a balanced output. The core of my transformer will be made of these two pieces of ferrite material. Ferrite is a ceramic compound made from iron oxide, manganese, and zinc. It has a relative permeability of 2300 and a resistivity of 6.5 ohm meters. The two pieces are identical. It comes in two pieces to facilitate the winding of the primary around one side and the secondary around the other side. The two pieces are then put together so that the magnetic flux from the primary side can be channeled into the secondary side. I will use magnet wire to wind my transformer. My primary will consist of 5 turns, and if I point my right thumb down, the fingers of my right hand will wrap around in the direction I will wind the primary. Besides being used to wind transformers, magnet wire is used to wind motors and generators. It has an enamel insulating coating on it that has to be removed to make electrical connection to the wire. Here is my completed primary consisting of 5 turns. I will now wind the secondary, and it will consist of 10 turns. I will wind it in the opposite direction. So now if I point my right thumb up, my right fingers will wrap around in the direction that I will wind the secondary. Here is the completed primary with 5 turns and the secondary with 10 turns. If you look down from the top, the primary is wound clockwise and the secondary is wound counterclockwise. Here is an illustration of our transformer with our 5-turn primary and our 10-turn secondary. And looking down from the top, the primary is going around clockwise and the secondary is going around counterclockwise. I have an Analog Discovery 2. It has a 2-input oscilloscope that displays on my laptop. It has a function generator that I'm applying to the input of our transformer, and I'm applying a 1 volt, 1 megahertz signal. The top display is the primary, the bottom display is the secondary. We see the 1 volt amplitude, 1 megahertz signal applied to the primary. The secondary is a 1 megahertz signal of 2 volts amplitude, and notice the two signals are in phase. If I take the two pieces of the transformer and start to separate them, we see that the secondary voltage drops. That's because all of the magnetic flux coming from the primary is no longer getting channeled into the secondary. With 5 turns on the primary and 10 turns on the secondary voltage is twice the primary voltage. If we were to look at currents, we would see that the secondary current is 1/2 the primary current. That way the power coming out of the transformer is the same as the power going into the transformer. The primary and secondary signals are in phase. I have wound another secondary that I've wound in the opposite direction. Let's switch secondaries and see what happens. Here is an illustration. Our secondary, looking down from the top, is wound counterclockwise, and we're going to replace it with a secondary that is wound clockwise, just like the primary. Now with the secondary wound in the opposite direction, we still see we double the output voltage, the voltage on the secondary, but now the two signals between the primary and the secondary are 180 degrees out of phase. Later we will apply Faraday's law to explain the effect of the number of turns on the voltage between the secondary and the primary, and we will also explain the effect of the direction of the turns on the phase between the primary and the secondary. Before we do that, let's build a transformer with what we call a balanced output. This is the wire that I'm going to use to wind the secondary of our balanced output transformer. In the very center of the wire, I've removed the insulation so that I can make an electrical connection to it with this second wire. Here is our transformer with a 12-turn primary and a 6-turn secondary. So this will be a step-down transformer. The output voltage will be lower than the input voltage, and the secondary has an electrical connection to the middle of the windings. Here is an illustration of our transformer showing the 12 turns of the primary wound clockwise looking down from the top. Here is the 6 turns of the secondary looking down from the top is wound counterclockwise, and there is an electrical connection to the middle of the windings on the secondary. We will ground one terminal of the primary and the center connection to the secondary. That way we will have an unbalanced input and a balanced output. These transformers are sometimes called baluns, B-A-L-U-N, where you have a balanced signal on one side and an unbalanced signal on the other side. I will now apply an AC signal to the primary and look at the output between the top terminal of the secondary and ground. The top trace is the signal being applied to the primary. It is a 1 megahertz sine wave with an amplitude of 4 volts. The bottom trace is the output, and it is taken between the top terminal of the secondary and the connection to the middle of the secondary. The output has an amplitude of 1 volt, so we are stepping down the voltage from the 4 volt amplitude input to the 1 volt amplitude output. This makes sense because the primary has 12 turns and the secondary has 3 turns between the top terminal and the connection to the middle of the secondary. Also notice that the input and output signals are in phase. With an AC signal applied to the primary, let's look at the signal between the top terminal and ground and the bottom terminal and ground of the secondary. The bottom terminal of the primary and the connection to the center of the secondary are grounded. Applied to the top terminal of the primary is a sine wave of frequency 1 megahertz and amplitude 4 volts. The signal between the top terminal and ground of our secondary will be displayed on one channel of our oscilloscope, and the signal between the bottom terminal and ground will be displayed on the other channel of our oscilloscope. I've changed the scale to 1 volt per division. The top trace is the output from the top terminal to ground of the secondary. It has an amplitude of 1 volt. The bottom trace is the signal coming from the bottom terminal to ground of the secondary, and it also has an amplitude of 1 volt. And you can see that the two signals are 180 degrees out of phase. With an AC signal applied to the primary, let's look at the signal between the top and bottom terminals of the secondary. The bottom channel is displaying the signal between the top terminal and ground of our secondary. It is a 1 volt amplitude sine wave, as we've seen before. The top trace is the signal between the top terminal and the bottom terminal of the secondary. And we see we're getting a sine wave with an amplitude of 2 volts. With 12 turns on the primary and 6 turns on the secondary, we expect a step down in the voltage by a factor of 2. And that is what we're seeing. We're inputting to the primary a sine wave with an amplitude of 4 volts, and the sine wave output across the secondary has an amplitude of 2 volts. An example of a transformer with a balanced output are the canister-shaped pole-mounted power distribution transformers you see all over North America. These top two feeds are the connection to the primary. The 7.2 kilovolt line voltage is attached to one, and the other one is grounded. These three terminals are the connections to the secondary. The left and right one are the electrical connections to the two ends of the secondary, and the middle one here is the electrical connection to the center of the secondary. The center connection is going to be grounded. Here is an illustration showing the 7.2 kilovolt line feed to the primary. The electrical connections to the two ends of the secondary are referred to as hot wires. The electrical connection to the center of the secondary is referred to as the neutral wire. The turns ratio between the primary and secondary is 30:1. So if you wire a receptacle with either hot wire and the neutral wire, you will have a 120 volt receptacle. If you wire the receptacle with the two hot wires, you will have a 240 volt receptacle. Another example where a balun transformer is used is when you have an unbalanced signal that you want to feed to a dipole antenna. Here we have an unbalanced signal coming from a coaxial cable where the outer sheath of the coaxial cable is grounded. This signal is fed into the primary of our transformer. The output of the transformer, the two ends, are connected to the dipole antenna. The center connection can either be grounded or left open. We are going to use Faraday's law to understand the operation of a transformer. We will look at a transformer where the primary windings and the secondary windings are in opposite directions, and one where the primary windings and the secondary windings are in the same direction. We will apply a sinusoidal source to the primary, and across the secondary there will be the load resistor R sub L. We will assume that the ferrite core channels all of the magnetic flux from the primary into the secondary. The primary magnetic flux is phi sub P, and we will define it as pointing up. The magnetic flux in the secondary we will define as phi sub S, and it's also pointing up. So phi sub P is equal to minus phi sub S. Here is Faraday's law. On the left-hand side, we're taking the integral of E dot dl around a closed path. On the right-hand side, this d lambda dt is the change in flux linkage with respect to time through the surface whose perimeter is defined by the path of integration of E dot dl on the left-hand side. If you put the fingers of your right hand in the direction of the integral of E dot dl, you want to determine the change in flux linkage with respect to time in the direction of your right thumb. Let's now apply Faraday's law to our two transformers. We are going to assume that the magnetic flux going through these areas of our two transformers will be negligible compared to the flux linkage through the primary and secondary windings of our two transformers. Applying Faraday's law to the primary, we're going to integrate E dot dl such that we go counterclockwise through the coil and around our circuit. Our right thumb will point up, so we will be calculating the d lambda dt in the direction of phi sub p. And we will have the exact same equation for applying Faraday's law to our primary on our second transformer. Applying Faraday's law to our secondaries, in both cases we are going to integrate in the counterclockwise direction through the secondaries, so our right thumbs will be pointing in the direction of phi sub s. So the change in flux linkage with respect to time in the secondaries that we will be calculating will be in the direction of phi sub s. The flux linkage in the primary will be the number of turns N sub p in the primary times the magnetic flux phi sub p in the primary. The flux linkage in the secondary will be the number of turns in the secondary, N sub s, times the magnetic flux in the secondary, phi sub s. We are going to assume that the wires making the connections and windings have negligible resistance so that we can approximate the integral of E dot dl in all the wires as 0. Integrating E dot dl in our primaries, let's start at the bottom of our power supply. So the integral of E dot dl will be 0 until we get to the top of the power supply. So we'll have 0 plus V sub P as we go through the power supply. For the secondaries, the voltage across our load is V sub S. So starting at the top of the resistor for the transformer on the left, as we integrate E dot dl through our windings, we get 0, and as we go through the load resistor, we get minus V sub S. For the transformer on the right, let's start at the bottom of our load resistor. As we integrate through our windings, we get 0, and as we integrate E dot dl through the resistor, we get plus V sub S. For both primaries, we have V sub P is equal to minus the number of turns in the primary times the change in magnetic flux with respect to time in the primary. Since phi sub P is equal to minus phi sub S, in the secondary we're going to replace d phi sub S dt with minus d phi sub P dt. For the transformer on the left, we have minus the source voltage is equal to the number of turns in the secondary times the change in magnetic flux in the primary with respect to time. For the transformer on the right, we have the source voltage is equal to the number of turns in the secondary times the change in magnetic flux in the primary with respect to time. From these two equations for the transformer on the left, we see that the ratio of the secondary voltage to the primary voltage is equal to the number of turns in the secondary divided by the number of turns in the primary. From these two equations, we see that the voltage in the secondary over the voltage in the primary is equal to minus the number of turns in the secondary over the number of turns in the primary. When the windings in the primary and the secondary are in opposite directions, the secondary voltage is in phase with the primary voltage. When the windings of the secondary and primary are in the same directions, the secondary voltage and the primary voltage are 180 degrees out of phase. We can step the secondary voltage up or down from the primary voltage with the ratio of the number of turns in the secondary to the number of turns in the primary. Assuming no loss of power in the transformer, the power into the transformer is going to equal the power out of the transformer. The power in is just the product of the current and voltage in the primary, and the power out is just the product of the current and voltage in the secondary. So the ratio of the secondary voltage to the primary voltage is equal to the ratio of the primary current to the secondary current. Using our relationship for the voltage in the secondary to the voltage in the primary and our relationship for the voltages and currents in the secondary and primary, we find that the ratio of the current in the secondary to the current in the primary equals the number of turns in the primary to the number of turns in the secondary. So if we're stepping up the voltage in the secondary from the voltage in the primary, we're stepping down the current in the secondary to the current in the primary by the same amount. Using these two equations, let's look at another application of transformers to transform impedances. Here we have a transformer with the load resistor and our equations for relating the secondary and primary voltages and currents. The input resistance to our transformer will be the ratio of the primary voltage to the primary current. Using this equation, I can rewrite the primary voltage in terms of the secondary voltage, and using this equation, I can rewrite the primary current in terms of the secondary current. I have the ratio of the secondary voltage to the secondary current. That's just the load resistance R sub L. So the resistance looking into our transformer is just the load resistance times the square of the ratio of the turns in the primary to the turns in the secondary. Let's look at an example where we have 12 turns in the primary, 6 turns in the secondary, and our load resistance on the secondary is 12.5 ohms. The resulting resistance looking into the transformer then is 50 ohms. If we had a 50 ohm transmission line and a 12.5 ohm load, we could use this transformer to do impedance matching between our transmission line and our load resistance. The war of the currents involved how electrical power was going to be distributed. Was it going to be distributed by DC or by AC? And the transformer played an important role. Nikola Tesla grew up in Serbia, and he was educated as an electrical engineer. And he went to work for the Edison company in France and eventually moved to the U.S. to work directly with Thomas Edison. Edison was developing electrical power distribution systems based on DC. Edison told Tesla that if he improved the efficiency of the DC dynamo, the device for generating DC electricity, he would give him $50,000. Tesla got the dynamo to the efficiency that Edison asked for, and then asked for his $50,000. Edison's response was, "You don't understand American humor. I was joking." So Tesla quit, and he had difficulty finding employment. For a while, he was employed digging ditches. So back then, you'd have to manually dig ditches for laying pipes in cities. Eventually, George Westinghouse hired Tesla, and they started to develop an AC power distribution system. Edison's DC power distribution system had limited range because of the I²R losses in the wires carrying the electrical power. With transformers, Westinghouse and Tesla could step up the voltage and step down the current, thereby greatly reducing the I²R losses in the wires carrying their AC power. So they could distribute their AC power over much greater distances than Edison could do with his DC power. Then at the point of use, they could use transformers to now step down the voltage. With this advantage, the AC system became the accepted method for power distribution. In the 1890s, there was not a comparable technology for stepping up and down DC voltages as there was with the use of transformers for AC. Today, with power switching transistors, power plants can convert AC power to high voltage DC for transmission, which is then stepped down with power switching transistors to low voltage AC at the point of use. There are several advantages for power distribution with DC compared to AC, which I won't go into as that would be the subject of a video by itself. If you are interested, there is an article in the August 2015 issue of IEEE Spectrum that talks about high voltage DC long distance power transmission systems that are being built or have been built. This figure is of an almost 1,700 kilometer DC power transmission system to take power from a hydroelectric plant in China to Zhejiang province. There is a high voltage DC link between France and Spain with a converter station like the one pictured here at both ends of the high voltage DC line.